So you might think when you learn to drive that when you press the gas pedal in your car that there's just some force from the engine which propels the car forward. But I would argue that that's an internal force, and it can't be on the free body diagram for the car. You need some external force to actually propel the car here on Earth. Only external forces from the environment on the car can affect its acceleration. So what the engine does is it rotates the wheels. So you've got some torque maybe on the back wheels here, which cause it to go or accelerate, have, I guess, angular acceleration, which would be clockwise. And then what that does is it tries to push backwards on the ground, but it doesn't because it's static friction, prevents it from screeching along. So if you were on pure ice, it would go like this. You wouldn't go anywhere. But the friction kind of locks it in, and then there's a forward force by Newton's third law of the static friction of the road on the tire, and that's actually what gets your car going. For static friction of the ground on the wheels, I guess. So I would argue that no matter how fast this car is going, there's 4 points on the car that are at rest, and those are the bottoms of the wheels. If it was just a wheel spinning like this, then the top, this piece of tape, is going to the right at the top, and it's going to the left at the bottom. And so if I move this whole wheel along towards the right and add those two velocities, so the axle is moving this, then just at the moment when this piece of tape is at the bottom, the motion to the right of the axle cancels the motion to the left of the tape, and it's at rest momentarily. And that's exactly what rolling without slipping does. The bottom points are at rest. And I guess the top points are going twice as fast. If this car is going 100 kilometers an hour, the tops of the wheels are going 200 kilometers an hour because there's the motion of the axle and that spinning motion. So that's how it sort of compensates. I also try to think of, if you think of a tank tread or something, a continuous track, as it's called, you can imagine it rolling along, and there might even be spikes or something that come out and like dig into the ground as it rolls over it. And certainly those spikes are not sliding. Right there. And then I think the wheel is the same sort of thing. Bottom of the wheel is at rest relative to the ground as it rolls. Another way of looking at it, what if I have a triangle and I rotate it? The bottom of the triangle, where it touches the ground, is a fixed point. It's the center of rotation. Makes sense? Okay. So what if I had a square and I rotate that? The bottom point is a fixed point, it doesn't move, right? Well, what if I had an octagon? The bottom is a fixed point. So what I'd say the wheel is just a infinity-sided polygon. So it's whatever the bottom point is never moving. You're always rotating around the bottom point. It's just that the location of that bottom point changes with time. Marble rolling without slipping. So he's going to release the marble. As it goes along, you can kind of see the bottom. He just pushed the marble, and yet the bottom sticks, and so it rolls. Off it goes. If you had a surface, so this is just a pan with ice, right? Okay. And is it on a tilt, or do you kind of push it?
It's on a very slight tilt.
Very slight tilt. He releases it. Look at the marble go. It slides. This is called sliding without rolling, or slipping without rolling, I guess. No friction. There's no reason for it to start actually picking up its rotation. It just slides along. Seems like a great party trick. We have so many of these. Slipping without rolling. I love that demo. And this is showing, I guess, another one. The tire lifting off the road, making new contact, not moving. That's thing A. Thing B is that if you've got a torque on that engine, if the tire turns faster, it pushes harder on the road, and the road pushes forward on it. And this is actually braking, as in C. The tire is moving to the right, and you apply the brakes. So you apply a torque which wants to slow the rotation of the tire. Then, if the tire turns slower, it pulls forward on the road, and the road actually, you can slow down your car this way. keep that in the slides. This is the bowling ball experiment where what we are going to do, we're going to do this in practicals at some point. Probably not this week because we have a mock quiz this week, but when you come back after Thanksgiving, you can try this out where you send the bowling ball along and then you try to get it to move in a circular path. And if you know the center of the circle, you have to hit it towards the center of the circular motion. So that's one little hint. Another one is this one. And just hold the backpack and try to spin it around in a circle and try to think of the force to keep it in a circular path, just in a big circle. All right. Hold the bag, swing it in a horizontal circle at a constant speed, so you're pulling towards, again, the center of circular motion. So my hypothesis is that anytime any object moves in a circle, then the sum of all the forces exerted on it by outward objects must be directed towards the center of the circle. If it's a hammer, or if it's your arm, the force of your arm is sort of a tension. Every curve has some sort of radius. So this is an intersection of Highway 27 and Highway 401. There's the sort of on-ramp, which might have a radius of 75 meters. Maybe another portion of a curve, which has a radius of 410 meters. Another portion of a curve. What I would say is any time you are turning, you can possibly fit your path to being a portion of a circular path. And so you hear in these physics problems a lot that the radius of curvature of the road was 75 meters or something. So what that's telling you is that it doesn't mean the road is always a circle, but if you're on that path and you pretend you're on a circular path for at least a certain amount, then the radius tells you how tight the turn is. Smaller the radius, the more you have to turn to stay on the road. And a smooth curve has a large radius. So that's important. And then there's acceleration vectors. So what I would say, if you have an object, let's say, that's moving along, and here's its path, like that. You could draw the path in blue, for example. And you look at it at maybe this point right here. Well, we can draw maybe in green that has a velocity vector, which is always tangent to the path. Well, then you have actually two acceleration components. There's a parallel, which is in the direction of the velocity, and a perpendicular, which is towards the center of the circular path. And so the real acceleration vector is somewhere like this. This is acceleration. So the acceleration is equal to the vector sum of a parallel plus a perpendicular. A parallel causes the object to speed up. A perpendicular causes the object to turn left. They both have units of meters per second squared, as it turns out. They are just two components to the actual acceleration, which is on this weird diagonal. But here you have an object which is both speeding up and turning. And so there's two components to the acceleration. An object that's changing direction must always have some perpendicular component to its acceleration so that it can change the direction of the velocity vector, that tangential velocity. Otherwise, it's going to stay in a straight line. So that's how we look at acceleration. The book starts off with a bunch of stuff about thetas and radians, so let's go through that. There's something called rotational angle and angular velocity. So let's start with rotational angle. So this is talking about, I think one of the best ways to visualize that is to go back to this wheel and say, okay, let's look at this orange piece of tape on the wheel. Well, if it changes its position by that much, you can measure it away like counterclockwise from the x-axis as having turned some angle theta, where the center of the triangle, the vertex is down here at the center of rotation, and it's moved now some angle theta. So you can use theta to specify its position. And the distance it travels, this arc length, it's going to be, if it goes all the way around, it'll be 2 pi times the radius, right? It'll be the circumference. So we can use a dimensionless angle unit called radians, where you say 2 pi radians is the angle it goes around for one whole circle. That's the definition of radian. So then you can use this equation. The arc length is equal to r times theta. So if theta is 2 pi, that means it went all the way around the circle. The arc length was the circumference 2 pi r. That's how that works. So it's a nice way of measuring angles. Once you do that, there's something called omega, which is the change. Delta theta divided by delta time. And its units are radians per second. So if you take the amount of time it takes to go a certain delta theta and divide by that time, to divide delta theta by the time, you get omega in radians per second. And it turns out that now you can find that tangential speed as being omega times r. So it's just a handy way of describing circular motion, so something that's going on a circular path. And we had on this morning's pre-class survey this question: you drive halfway around a circular track in 30 seconds, what was your angular velocity? So halfway around means that delta theta is equal to 2 pi, is all the way around divided by 2. It's pi radians. And 30 seconds, delta t is equal to 30 seconds. So omega is delta theta divided by delta t is equal to 3.14 radians divided by 30 seconds, and you get 0.105 radians per second. If you're going on a circular path, this is the diagram you have in your book, is that the velocity v1 and v2, if you're doing a uniform motion where the speed is not changing, then the velocity vectors stay the same length, but they change their direction. So if you go delta theta from here to here, your velocity has changed by delta theta. And so I would argue that this green triangle and this red triangle are similar triangles. And what that means is that delta v over this whole actual velocity v is the same as delta r, delta s, the arc length, divided by this distance r. And you can solve that around for delta v, and then you can use the equation for acceleration is delta v over delta t. So it's v over r times delta s over t, and that's just v. So you end up with v squared over r as your centripetal acceleration. It's the acceleration you need to stay on a circular path. In order to do that, you need to have a net force which is pulling you towards the center of that circular path, and that's the centripetal force you put in your backpack when you're spinning it around. So I want to talk a little bit about these fictitious forces and the kind of warning label on Newton's laws is that they only apply in inertial reference frames, where an inertial reference frame just means a reference frame that is not accelerating. So, for example, this room is an inertial reference frame, pretty much. I guess maybe the Earth's orbiting the sun or something, but we consider this to be an inertial reference frame, not accelerating. Even if you were on the back of a truck or something, had your lab set up and that truck was going at a constant velocity in a straight line, that would be an inertial reference frame. And there's this idea that there's no experiment you can do in the back of that truck to prove whether it's moving or perfectly stationary, because all velocities are relative. But if it's accelerating, then you can definitely figure that out. And here's a little video showing a coffee cup. First, you're going to see the coffee cup from the perspective of the person in the car, and they step on the gas. And what's interesting is there's the coffee cup's on the dash, they step on the gas, and then the coffee cup just jumps right into her lap. It's like it jumps backwards. But if you look at it from the side, what happens is that it actually just moves forward. Idea being that in the accelerating reference frame of inside the car, there seems to be this weird fictitious force that pushes coffee backwards into your lap. But from the real life version, then all that's happening is that the bottom is being pulled to the right, and then that causes the coffee to fall. So, and this is, same thing happens when you're slowing down. If you're slowing down, you feel this forward force pulling you towards the front of the car. Like if you smash into a brick wall, you might even fly right through the windshield. But I would say there really is no forward force on you when you're slowing down. Some physics teachers, not me, would describe this in terms of fictitious forces. But what a fictitious force does is it helps you describe motion when measured in a non-inertial reference frame. And it's okay to do that, I guess, but in this course it's much better to just always do your Newton's laws and your free body diagrams in an inertial reference frame. Just switch to an inertial reference frame and then analyze it, and I think it's a lot better that way. And then you don't ever have fictitious forces on your diagram. All that's happening here is that from the lab frame, there is a force backwards on the person, or backwards on the car, I guess, and that the person might continue on with their inertia forwards. So, example, the system would be the passenger here. And so if you're going to draw a free body diagram of the passenger, you would say, well, there's the normal force upward, there's going to be the gravity force downwards, and then if you're accelerating to the left, there's going to be a force of like the seat on the passenger that's backwards in the direction of acceleration. And so then that's what gives this acceleration is to the left. If you're turning a corner, then I remember this when I was a kid. I was sitting in the back seat, and they used to have these bench seats back in the old days, and we never used to wear seatbelts back in the 70s. There were no seatbelts. When my parents would turn left, I would get pushed into my sister on the right. And then if they turned right, my sister would get pushed into me on the left. So you tend to get thrown towards the outside. And that's called centrifugal force. But, again, you're in a non-inertial reference frame. You're accelerating towards the center of a circular path. And similarly to if you drive forward, the coffee feels this fictitious force backwards. If you're accelerating towards the center of a circular path, you're going to feel a fictitious force towards the outside of the circular path, away from the center. But what's really happening is that you just want to continue in a constant velocity in a straight line unless there's an external force. So you would go off into the ditch if you were moving straight ahead, and yet the whole car is turning to the left, so you feel pulled towards the right a little. Somebody asked, why is centrifugal force classified as a fictitious force when we can actually see it with objects? And here's a centrifuge, and you can buy these. They cost a lot of money, and you stick a test tube in there, and boom, it settles any kind of, sediments or something go right down to the bottom of that test tube. And so it's centrifugal force is very useful. We use it all the time, but it's not real. You don't draw it on a free body diagram, but you certainly do feel it. Okay, you guys want to see me take this hot coffee and swing it over my head? It is kind of hot. Let's take the lid off for extra fun. You can see that this is full of coffee. See, full of coffee. Okay, this hot coffee. Now I'm going to put it on this platform, swing it over my head, and maybe get drenched in coffee. Let's see what happens here. Look good? 1, 2, 3. Let's take another sip. Another good party trick. We're all about the party tricks here in physics. So, yeah, basically, how could it be? Well, this is, again, this centrifugal force. What's happening is that the coffee is getting pulled towards the outside of that circle in such a way that it doesn't fall. And we're going to work out what this minimum force is in a bit, but basically this could also happen when a car is driving on a loop-de-loop or something. If you're going fast enough, or a motorcycle, you can go right around. And that's when your speed is greater than this minimum speed, then it requires an extra normal force downwards in addition to the gravity to keep you on that circular path. And that's what's happening with the coffee. I swing it so fast that not only does it need gravity to pull it down, it also needs like the whole force of the cup and the tension and all that. Otherwise, the coffee would, I guess, go off in a sideways direction. So to stay in the cup, or to stay on the circular path, it has to stay in the cup. And the point of this loop-to-loop is that normal force must always be away from the surface. So if the surface is above you, the normal force is pointing down. It can never be into the surface unless your surface is covered in glue or something. There is going to be some minimum speed at which the normal force goes to 0. And if you're less than the minimum force, like if I do this not fast enough, so this is the thing, if you should practice at home, then it does fall. You turn into a projectile. You can't have a negative, well, I guess you can't have negative tension in this case, and you can't have a negative normal force on the loop-to-loop. When drawing a free body diagram for an object traveling on any circular path, which way do you draw the centrifugal force? And the answers were towards the center of the circular path, away from the center of the circular path, tangent to the circular path in the direction of motion, tangent to the circular path opposite the direction of motion, or trick question, the centrifugal force is fictitious, and so it isn't drawn on a free body diagram. The next question, or previous question, was when drawing a free body diagram for an object traveling on a circular path, which way do you draw the centripetal force? Towards the center, away from the center, forward, backward, or trick question? The centripetal force is the net force. And you don't draw the net force as one of the forces on the free body diagram, if that makes sense. Sometimes I do draw the net force as kind of off to the side or something. I usually draw it as the acceleration. But on the free body diagram itself, you don't put net force. Net force is the sum of all the forces that are on the free body diagram. A 1 kilogram ball on a string is whirled in a vertical circular path with a radius of 1 meter. So at the top of its path, it is traveling with a speed of 5 meters per second. So v is equal to 5.0 meters per second. What is the tension in the string in this moment? So there's the tension. It's got some radius is equal to 1.0 meters. Let's do a free body diagram of the ball. So that's the object. I think I'm also going to mention, as I'm drawing this, as where it is, because it goes in a circular path. So I'll just say free body diagram of ball at the top of the path. So there's tension acting down, and there's the weight also acting down. And remember Newton's second law, F net equals the mass times A. Okay, so what I think is going on here is that there's centripetal force acting down. So there's a lot of ways you can solve this. One of the ways I kind of like to do this is I define this axis, the R axis, as being towards the center of circular motion. So let's define plus R direction as toward the center of the circular path. Somebody actually put in the pre-class survey, can you write more neatly? Sorry about that. I can try. Starting now. Newton's second law. So what we do is let's define plus R as being downward in this case. Since we're at the top of the path, the center of the circular motion is actually down in this case. So if we do F net in the R direction is equal to M times AR, this is centripetal. It's the same thing. This is V squared over R. That's the centripetal acceleration. And the forces here is just going to be weight plus the tension, since these are both down. So it's mg plus t is equal to mv squared over r, and so t is equal to mv squared over r minus mg. So it's t is equal to 1.0 times 5 squared divided by 1 minus 1.0 times 9.8, and I got the tension is 15.2 newtons. There's probably a minimum speed, right, beyond which it's going to fall or something. So let's calculate that. A 1 kilogram ball on a string is whirled in vertical circular path, radius of 1 meter, same exact diagram. What is the minimum speed the ball can have at the top of its path in order to stay on the circular path? So the way I draw that, again, same sort of thing. There's t. Now v is what you don't know. Here's the radius is 1 meter again. And what I would say here is that I think the faster the speed, the higher the tension. If I really whip that ball around at a very, very fast speed, it's going to take a lot of tension in the string to make that happen, until maybe the string would even break if you do it too fast. So my strategy here is let's reduce the tension to 0. I think the minimum speed will be when t equals 0. So if we draw the free body diagram, let's think of all the forces that are on the ball. Well, there's gravity, the weight, and that's it. Only one force. It actually looks a lot like projectile motion. But anyway, that's it. So what we do is, once again, F net in the r direction is equal to mass times a in the r direction, the centripetal in both cases. So this is v squared over r, this is m. And then you just put all the forces, it's just weight, I guess. Let's define plus r to be down, because that's towards the center of the circular path. mg is equal to mv squared over r. The m's cancel, and you get that v squared is equal to g times r, and v, the minimum, is equal to the square root of g times r. In this case is equal to the square root of 9.8 times 1.0, and you get v min is equal to 3.1. For a 1 meter string, it's 3.1 meters per second. It's all about drawing these free body diagrams. So like the centrifugal force, the Coriolis force is a fictitious force that comes from being in a non-inertial reference frame, one that is accelerating, first described by a guy named Coriolis. So when your frame is rotating, then, and an object has a velocity in the rotating frame, then it tends to turn. And the turning is that if the reference frame is rotating clockwise, then an object tends to deflect towards the left. So it has an acceleration caused by the Coriolis force, this fictitious force that takes us to the left. If the reference frame is rotating counterclockwise, the deflection is to the right. And I've given a link to a animation, which looks like this, where what we're going to do is shoot the ball in a straight line. So if you look really carefully, it's going to go in a straight line. But since the Earth is rotating underneath it, that's the straight line, if you can believe me, it looks like it's curving to the right. So your reference frame is rotating counterclockwise, and the thing is bending towards the right. So that's called Coriolis. Again, fictitious force. If there's a low pressure zone and you've got air moving from all sides towards the center, and for example, if you're in the northern hemisphere, if you think about it, is rotating counterclockwise because it rotates towards the east. Sunrise is in the east. Then Coriolis in the northern hemisphere bends all this motion to the right. So the stuff coming from one side goes to the right, from the east, from the north it goes that way. So what it does is it spins hurricanes counterclockwise in the northern hemisphere. And there's one, this is actually not Milton, this is the one that hit Florida 2 weeks ago. So in the northern hemisphere, all hurricanes, because they are low pressure zones, that's where the storm forms, go counterclockwise. In the southern hemisphere, all the hurricanes go the opposite direction, clockwise. And it is impossible for a hurricane to cross the equator, because the hurricanes are basically caused by the Coriolis force. And so, unfortunately, right now, today, this exact same thing is happening in Florida. Should hit sometime around 1 o'clock in the morning. It hits Tampa, I think, which is not good. And we think that global climate change, which is caused by air pollution, is warming waters, making these kinds of hurricanes more powerful and more frequent. Okay, so the way you do these banked curve things, there's 2 diagrams you can draw. And in order to envision, so you got a curve of radius 70 meters. In order to envision that circular path, you have to think of a top view, okay? Which is, there's the circle, and the radius of the circle is, there's the center there. You put r is equal to 70 meters. Oops, sorry. And you've got a car here. I'll draw it like this. It's going at some speed, v0. And it says, at what speed can a car take this curve without assistance from friction? And it's banked at a 15-degree angle. So in order to see the banking, you have to then draw the rear view, which is, it's a little hard to picture, but in this case, what you've got is something that looks like this. Here's your angle of theta is equal to 15 degrees. And here is your car kind of looked at from behind. I don't know, there's the window or something. It's going into the page. So I would say that this direction off to the left is your plus r direction because it's towards the center of the circular path. So I will define plus r equals to the left. So you have to imagine that this car is going around in a great big horizontal circle. So the direction of centripetal acceleration is towards the center of that circle. So it's not tilted, it's directly towards the left, even though there's a banking angle. So then you draw the free body diagram of the car, and I'm going to say from the rear view. It doesn't help much if you do the top view free body diagram, because then gravity is into the floor and normal force is coming out. And so you have to do the rear view, and then it's not too bad. You just have this. You have normal force going up like that on a diagonal, and you have the weight going down. And I guess you could put, I don't know, define plus y is up maybe. And remember, plus r is to the left. So there's no x-axis here. There's an r-axis. And you say a sub r is the centripetal. It's v squared over r. And a sub y is 0 because the car is staying on a horizontal circle. It's not accelerating up or down. And unfortunately, you have to decompose your normal force in this case. And it's hard to find where the angle theta is. But remember, this is horizontal. This is theta. So I think this is 90 minus theta. And then if you tilt your head, the normal force is perpendicular to the surface. So this is going to be, 90 minus theta. Anyway, it's theta. And this is the normal force. This is the normal force in the r direction. And this is the normal force in the y direction. And so you can use your SOHCAHTOA thingies to solve out. What you get is that n sub r is equal to n sine theta, I think. And n sub y is equal to n cos theta. So n is the thing you don't know. It's a normal force. You have to solve for it. But you do know that F net in the y direction is the mass times the acceleration in the y direction. So that's going to be n cos theta minus mg, because the y component of the gravity is negative mg, and that should equal 0. Because there's no y acceleration. So the normal force here is equal to mg divided by cos theta. But again, there's never an equation for normal force. You just have to kind of solve it out somehow. And also, the Newton's second law in the r direction is m times a sub r. So it's just n sine theta is the only horizontal force. And then m times v squared over r. And now you can take this equation for normal force that you got from balancing the y components and just plug it in here, and then the whole thing works out. So you've got m times g divided by cos theta times sine theta is equal to m times v0 squared divided by r. The m's cancel, so m on that side, divide both sides by m, basically. And then you can also note, if you want, that the trig identity that sine theta divided by cos theta is equal to tan theta. And so you get g times tan theta is equal to v0 squared divided by r. v0 squared is equal to gr tan theta. So this v0, the critical, is going to be the square root of gr tan theta, which is equal to the square root of 9.8 times 70 meters times tangent of 15 degrees. And you get 13, V0 equals 13.6 meters per second. So if you go exactly that speed, then the static friction could be 0. You could be on a perfectly slippery road, and the normal force only would allow you to go around. If you went any faster than that, I think you'd start to slide up the hill. If you went any slower than that, I think you'd slide down the hill, down the bank. All right, so this is this idea that the moon orbits the Earth about once per month. And apparently Isaac Newton, at some point, was coming up with his first law, was saying that if there's no net force on an object, it travels at a constant velocity in a straight line. And then he's looking at the moon and thinking, well, why does the moon orbit the Earth? Like, what's the net force there that could be pulling the moon towards the center of the Earth? And then an apple fell on his head, is the apocryphal story. Gravity, so this was this idea, Newton's kind of fourth law. It's this universal law of gravity, thank you. Gravity is an attractive long-range force between any two objects, and it's shown here as Fg of 2 on 1 and Fg of 1 on 2. They're equal and opposite. They're given by this equation, which is g times m1 times m2 divided by r squared, where r now is just a scalar distance between the two centers of the two objects. And then the capital G here is a universal constant, which is 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. So if you have, for example, two 1 kilogram masses located 1 meter apart, then the force between them of gravitational attraction would be 6.67 times 10 to the minus 11 newtons, which is very difficult to measure. So it's a very, very small force. From the pre-class survey, Earth and Moon rotate approximately around their center of mass. This makes sense for the Moon, but why is it so for Earth as well? So keep in mind that the force that's pulling the Moon towards the Earth is equal and opposite to the force that the Moon is pulling the Earth towards it. So in the two-body problem, both objects orbit around a common center of mass. Okay, so this is when they both have the same mass of 1 times 10 to the 24 kilograms. But if you make one of the masses twice as large, like 2 times as large or something, and we'll do circular orbit again, I guess, and start it. Now, the center of mass is closer to the black dot than the white dot, so it's a little closer, and its circular orbit here is smaller, half as small. You can make it even more, but the more and more massive you make the black dot, the smaller and smaller its orbit is. So until, if it's really like the Earth and the Moon, that's kind of more like what's happening with the Earth and the Moon, because the Earth is so much more massive than the Moon. The more massive object accelerates less and is closer to the center of mass. So the orbit of the Earth around the Earth-Moon center of mass system, people don't talk about it very much, but it is what causes the tides, actually. Unrelated, which forces contribute to the Earth's rotation about its axis? And so there are no forces that are needed to keep something rotating around its axis. That's conservation of angular momentum does that. It's like rotational inertia. Same as a top spinning, it just keeps on spinning, unless there's an external torque to stop it from spinning. So that's why we get a day-night cycle. I just wanted to mention you can, in Physics 224, measure the gravitational constant, capital G. You have to you get these two lead balls and you try to actually measure the force that's between them at a certain distance. And there's a torsion wire and a laser and all these things. You have to be really careful. If someone opens the door to the room, then the wind currents can throw off the whole experiment. So, you can measure it. So the gravity force is real. Let's do an example in which you've got an object with some unknown mass MO for object O, and it is sitting on the surface of a giant spherical rock which is floating in space. And the giant rock, which we'll call object E, has a mass of 6 times 10 to the 24 kilograms and a radius of 6,400 kilometers. What is the force of gravity of E on O? So I've worked that out in my calculator before I came to class. You use this equation, is capital G times the mass of one object times the mass of the other object, which we don't know, divided by r squared. So we're going to say Fg is equal to 6.67 times 10 to the minus 11 times 6 times 10 to the 24 kilograms divided by 6,400 times 10 to the 3 squared, and then MO. And if you work out all those numbers in your calculator, you get 9.8 MO, where that's in SI units. And can anybody think of a name? We need a name that starts with E, and it's a spherical object, and it's 6,400 kilometers in radius, and it has a mass of 6 times 10 to the 24 kilograms. Earth, we could call it Earth. Let's do that. I don't know. This equation is just a short form for the longer equation. When you happen to live on the surface of a large planet with radius r, mass me, like we do, then that equation becomes this equation where the lowercase g stands for uppercase G times the mass of the Earth divided by the radius of the Earth squared. Turns out to be 9.8. At sea level, it's 9.83. At up on the top of Mount Everest, it's 9.78 for this course. Let's just use 9.8. I think I put G equals 9.80 in case you're worried about significant figures. Curvature of the Earth. The idea here is that gravity is always pulling you towards the center of the Earth. And we've taken gravity as always being just straight down. So there's kind of a flat Earth approximation that we've been using. But it turns out that if you go sideways for about 8,000 meters, then the Earth curves and drops down by 5 meters. And what's interesting about that is that consider a ball that is launched exactly horizontally, so the initial y component of the velocity is 0. Well then, I would say that delta y is equal to a negative 1/2 g times t squared. So it's actually equal to negative 1/2 times 9.8 times 1 second squared, and you get negative 4.9 meters. So if I launched something sideways and it was going 8,000 meters per second, then in that 1 second it would have traveled down by about 4.9 meters, and it would be the same distance from the ground as it was when I launched it. So, and this is this idea that would be like thing D. Okay, it falls, as it's falling, it never doesn't get farther away from the Earth. It just goes around and eventually, so if I take this tennis ball and I throw it in that direction fast enough, then it'll go away, but eventually it'll come back and hit me in the back of the head. So that's an orbit. It's just 9.8 meters per second squared. That's exactly what these people up in the space station are doing. They have an altitude of 420 kilometers above the surface. Their speed is about 8,000 meters per second. That's exactly the speed you need so that you fall 5 meters for every 8,000 meters you go sideways. And then you're always the same distance from the surface of the Earth as you go. And if you do that, it takes you about an hour and a half to go all the way around the Earth. So that's what orbit is. There's right now a big crowd of people. There's usually around 3 people up there. Right now they have 11, I think. They're called Expedition 72, but they like to do things like astrobiology, astronomy, meteorology, physics. There's all sorts of experiments that you can do when you're in this microgravity environment. So let's actually calculate what the centripetal acceleration is. Well, we have an equation, v squared over r. We know that v is equal to 7.66 times 10 to the 3 meters per second. We can square that and divide by the radius of the orbit. The radius of the orbit is 6,790 times 10 to the 3 meters. And if you do that math, you actually get 8.6 meters per second squared. That's the centripetal acceleration toward the center of the circular path. The idea is that if you were in an elevator here on Earth and that elevator was accelerating downwards at 9.8 meters per second squared, then you would be in free fall. You would just be floating around the elevator, as would, any object that you're holding, like a baseball or something, would float in front of you. And you would feel completely weightless, at least for a while. But when you're up in space, they turn off all the rocket boosters, okay? It becomes very, very quiet. So it actually takes a while to get up to space. It takes a few minutes. But once they get up there and park themselves in orbit, they turn off all the engines and they just float around. It's very, very peaceful. They get a great view of the Earth if they look out the window, and things are just floating. And that is because they are in free fall. Now, it's not 9.8, it's only 8.6, but they're accelerating downwards at 8.6 meters per second squared, and that forms their centripetal acceleration. It's a really neat trick. I'll just put it here. Astronauts feel, and I'll put weightless in quotation marks because they have this almost the same weight as they do here on Earth because they are in free fall. Only gravity acts towards them, on them. There's no normal force, and so they just accelerate downwards. Question is, how fast would I have to drive my car in order to be weightless? No normal force needed to support your car. So, here's the Earth, here's your car, and here's your speed, v. And here's the center. Here's the plus r direction downwards. So this is the free body diagram of the car. So I'm going to do the weight, W equals mg. And what other force is acting on the car? They said the normal force is 0. And I'm going to neglect air resistance. And so in that case, you don't even need static friction. You're just driving at some speed. So that's it. So F net in the r direction is m times a sub r. So it's just mg is equal to m times v squared over r. The m's cancel. Doesn't matter how massive your car is. You're always going to have v is equal to the square root of g times r. So it's 9.8 times... So what is r in this case? Does anybody know what is this r? The radius of the Earth. You guys are following me. So my idea here is that you're driving around and around a circular path on the equator or something like that. I don't know, there's a road or something like that. And the center of the circular motion, so it's 6,400 kilometers. So I write sometimes 6,400 times 10 to the power 3 meters. And I get v is equal to 7,900 meters per second. So again, the same sort of 8,000 meters per second. So do you want to know what happens if you drive your car at 8,000 meters per second? It instantly vaporizes into plasma due to air resistance, okay? You can't do it. It just doesn't really work. Can't neglect air resistance at these kinds of speeds. Air resistance is almost totally absent. Even the ISS does experience some drag due to a little bit of atmosphere that's still up there, so they have these periodic boosts which keep them in a stable orbit. But it's pretty stable even without the boosts. Okay, I want to go back in time a little bit to way before Isaac Newton. 1609, sort of when the start of a lot of physics and astronomy was happening, when people who had telescopes, mostly for looking at other ships at sea, started looking at the sky with a telescope. And these are some of Galileo's sketches. Galileo noticed that if you look at the moon in a telescope, you see all these little craters. It looks like a place. So mountains and craters and shadows and things. That's interesting. Also, these little crescent-shaped things are pictures that Galileo drew of Venus. So Venus just looks like a star when you see it at night. But if you look at it in a telescope, it looks like a tiny, tiny little moon. And it goes through phases, just like the moon, as Venus orbits the sun. So that's interesting. And the other diagram here is showing Jupiter. If you look at Jupiter in a telescope, it looks like a little circle, and around it there's these 4 dots that move and seem to orbit around Jupiter. Those are the 4 Galilean moons of Jupiter. And at the same time, a contemporary of Galileo was Kepler, who was looking at, not with a telescope, but very careful observations of planets and how planets orbit around the sun. And he had a correct heliocentric model of the solar system in which the Earth was the 3rd planet around the sun, and all the planets we could observe were orbiting the sun. So Kepler wrote down these 3 Kepler's laws, again, well before Isaac Newton, to describe the shapes of the orbits and the periods of those orbits. So an ellipse is a mathematical shape. So if you take a piece of paper and you get a string and you put 2 tacks, you can form a kind of a triangle. Put the tacks in there. You take your pen and form a triangle, and then you can sketch a shape by just pulling that taut. You have to watch out for the knot. Move the knot away there. And just keep the string like that, and you go around, and this is called an ellipse. And if you take out these, then you have 2 tack holes. One is where the sun would be, and this is just called the secondary focus. There's nothing there. So it's a mathematical shape, and this would be a planetary orbit. So Kepler was a mathematician, knew a lot about shapes, and found out that ellipses were the shape of all the planetary orbits, including Earth's orbit around the sun. And so there's something here called perihelion when you're closest to the sun. And what's interesting about perihelion is that for Earth, perihelion happens on January 4th. So that's when we're closest to the sun. And then out here is called aphelion. Happens at July 4th. It's not the main reason that things are, that we get summer and winter here. There's a whole other reason. And how squishy the ellipse is based on how close these 2 foci are to each other. eccentricity tells you how squished the orbit is. And so most orbits, planetary orbits, have a low eccentricity, and so their path around the sun is almost circular. Mars is fairly eccentric, and also Pluto is quite eccentric. And a circle is a special case of an ellipse when the eccentricity is 0. You put both foci together. So Kepler's first law is that all the things that orbit the sun do so in elliptical paths. Kepler's second law is that a line drawn from the sun out to the planet sweeps out equal areas in equal times. And what that means is that these two areas are the same, so it's going faster at point A when you're near perihelion, and you're going slower out at point B when you're near aphelion. And the third law, which took actually into account analysis of many different planets' orbits, so it took him 10 more years to find this one, is that there is a relation between the square of a planet's period and the average distance it has from the sun, r. It's t squared equals r cubed, where t is the orbit of the planet in years, and r is the average distance from the sun in astronomical units, and c is some constant. So Kepler's laws were empirical, kind of like this equation we have for kinetic friction. It doesn't come from anywhere. It's just something that explains measurements. Kepler did not know why the planets moved in this way. And there were a lot of scientists around who were using these laws and trying to figure out what they were for. And in 1687, finally, Isaac Newton published one simple underlying theory which explained all of Kepler's laws, which Newton's laws of motion plus this Newton's law of gravity, and explains all of them. And it also explains these parabolic trajectories. I don't know where my tennis ball went, but if you throw things, we'll use the microphone, and you look at this parabolic path, this path is actually one little portion of an ellipse where if there weren't the Earth there, it would go all the way down and would travel around the other focus, which is the center of the Earth, and whip around really fast. And then as it comes here, a little tiny portion of that elliptical path looks like a parabola in our flat Earth approximation. The trajectories are only parabolic in the approximation that we neglect the curvature of the Earth and the variation in gravity with the distance from the center of the Earth.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.